Hello, Professor.
Hello, how are you guys?
Hello, Professor.
Hello. So we still have a few people coming in. 1, 2, 3, 4. Including tonight. See, tonight is the 16th, so we're continuing slender columns. And then we have 1, 2, 3, 4. So we have 4 more lectures after tonight. And of those 4, I've actually prepared 3. And then I just kept July 30th as a to be determined in case we run long on any of the next 3. And or if we want to just catch up time to talk about things or the final exam or whatever we want. So really, after tonight, we only have 3 more topics that we're going to tackle for this course. And those topics are going to be, again, after tonight, will be bond development of reinforcing bars, footings, and retaining walls. So we're getting there. Would anybody like to start off tonight with any questions that they had on what we've been talking about so far, or the homework, or just anything on your mind?
Professor, I had one
Yes.
quick question about the homework.
Sure. Did I lose him? That was a very quick question. I think we lost him. All right, well, he'll come back. Anybody else have any questions before Edgemond comes back? There he is. Edgemond, that question was way too quick. We lost you.
My internet connection decided to not help me out here. Okay, so the second problem on the homework, I just have a quick question. What does PG stand for?
Okay, let's see.
Because I couldn't find that in the lecture 10 notes where we just use the axial load, because we only have axial load on the second problem.
Yeah, okay. Find the size of column and rebar required. Oh, okay, all right. And actually, yeah, I didn't cover that. My fault. I mean, there's all these little nuances, so it's not terribly essential that I cover every single one of these. But yeah, I missed that one. So the G stands for gross. So what that is rho gross. And so what we're looking for is rho gross to be 2% of the column. And so because the reason why I have to give you rho gross is I didn't give you the size of the column, nor did I give you the size of the reinforcement. So you could satisfy the loads with a really big column and just a teeny little bit of rebar. Or you could satisfy the loads with a teeny little column and a whole mess of rebar, and there's an infinite number of answers in between. So if I staple down what the rho gross should be, then there's a unique answer to that problem. Now it's not a billion different combinations of more concrete, less steel, or less concrete and more steel. When I define how much steel there is as a fraction of the total column, then there's one unique answer.
And Professor, for reference, which lecture was this from? Because I couldn't find this in lecture 10, which we only covered axial load. But is it going to be in lecture 11? Because in lecture 11, that's when we went into a moment.
No,
So,
this is lecture 10.
Lecture 10?
This
But
is lecture 10.
we never used rho gross, that's why.
That's right.
I just don't know how to use this. I genuinely don't know how to use this.
Okay, well, no problem, no problem. We did briefly cover it in when I was going over, remember lecture 10, we talked about the mechanics for a little bit. We talked about P naught, PN, phi PN. We talked about that for a little while. But we also
Yes.
talked about all kinds of code prescriptions that I probably would have tuned out too. There's a lot of prescriptions in that lecture. And one of the prescriptions was that the ratio of steel to concrete has to be at least 1%, and it cannot be more than 8%. That ratio of steel to concrete is rho. And it's rho gross because it's the area of steel over the area of the concrete. Whereas in a beam, rho is area of steel over width times d. In a column, it is the area of steel over the width times the height. It's the gross area of concrete, not little d.
So pretty much it's going to be AG over
AST over AG.
AST over AG. Has to be 0.02.
Yes.
Okay, it makes so much more sense now. Thank you so much.
And it doesn't have to be exactly 0.002 or 2%, but that's your target. Just like we had targets when we were designing beams, your target is 2%.
2%. Okay. So, but whenever I'm getting the AG and the AST, that's going to be my design because that's when I have to pick, for example, if it's a 20 by 20, then I have to understand how many numbers I need for it to be 2%.
That's right. That's exactly right. But what you just said is an excellent example because you're not going to have exactly 2% because you're not going to pick a column that's 19.78 inches on side. See, you're going to pick a column that's going to be 20 by 20 or 22 by 22. And then you're going to pick 8 bars, but you have to choose between 8 number 8s, 8 number 9s, 8 number 10s. So the 2% is a target, but what you actually end up with is most definitely going to vary a little bit from the 2%. Not like 3%, but it's not going to be exactly 2%.
Okay, but so whenever I'm getting my AST and it's supposed to be, is it the same as how we did the beams of how we picked a little more? For example, if we got AST has to be like 9.44. Whenever I'm getting the bars, it has to be just a little more.
Yes.
And
yes.
then that's when I have to go back like that and try to get the column size to match.
Right. What you're actually going to do is you're going to look into your notes and find the equation for P naught. And in that equation for P naught, you had 0.85 F prime C, parentheses, area gross minus AST plus Fy times AST. Well, what you're going to do is you're going to substitute instead of AST, everywhere you see AST, I'm kind of giving away the whole problem, but you're going to put in 0.02 AG instead of AST and then solve for AG.
Ah.
Yeah,
Okay.
and then, but don't forget, everybody on the phone, please don't forget that once you come up with your trial size, okay, looks like 18 by 18 and 8 number 7s. Totally making this up, but whatever you come up with, then you have to check it. You have to calculate what phi PN is equal to and show that it's greater than PU.
Okay, makes sense. Makes so much sense now. Thank you so much.
Sure. Anybody else? Any other questions? Anything on your mind? Why is it so stinking hot? When's it going to be fall again?
I have one quick question pertaining to what you were just going over.
Sure.
So when you're doing this, like for problem number 2, you don't need to go back and check that you fulfilled your 2% steel. Do you just need to check the capacity?
Yes. Yes, I am totally okay with that because you're using 2% to find the area in the first place. That was your target. But then at some point in the game, you have to take what the numbers tell you is a minimum, and you have to pick something. So there are not an infinite, especially if I'm telling you it has to be 8 bars, then your choices are really 8 sevens, 8 8, 8 9, 8 10s. You have these quantum levels of steel, if you will. You can't get anything in between there. So you're going to target 2%, and you're going to solve for the minimum area of concrete, and then you're going to take 2% of that, and that's the minimum area of steel, and then you're going to pick something that makes sense. Again, so if you calculated 19.78 inches on square, you're not going to pick 19.78, you're going to round it up to 20. So Jeff, I believe Jeff, you're the one to ask the question. Once you choose something, 20 by 20, 8 number 9s, once you make your choice, don't go back and double check the 2% because it's not going to be 2%. It's going to be off by a little bit, but you do go back and make sure that phi PN is greater than PU.
Okay, got it. Thank you.
Okay, and then Jesus had typed in a question for me. Homework 6, problem 1. The solutions you shared had a beam with different dimensions that was assigned. Are you serious?
And also distributed load is different. It's 1 kip per linear foot instead of 2.
Okay, I don't doubt that. Homework number 6, problem number 1. I got 30 kips and I got 2 kips per lineal foot. I have 16 and I got 18, don't I? Was that the only problem with this?
And then with when doing the moment, it uses 1 kip instead of 2.
Okay. Oh, yes, it does. Yes, it does. Okay. All right. Apologize for that. Please use the solutions as a guide as to how to do it, but you're absolutely right. The numbers are going to be off. What I will do, so yeah, don't worry. I'm not going to grade you based on wrong answers, hopefully. So I'm going to redo it. Thank you for pointing it out. I will redo it and then use that as my answer key when I grade them this weekend. But in the meantime, please use my solutions as like a procedural guide, but as you've noted, the numbers will be off.
And for problem 2, we don't use I sub t, right?
Yeah, no. Problem 2, that really should be I gross or I cracked, not IT. T stands for transformed. I chose not to teach transform this time. I felt it would just add a complication without really adding value. So I dropped the whole speech on transform section properties. So anywhere that you see an IT, you can just substitute IG for I gross. And then when I did my solutions, I transformed them. Okay, well, I'll try to clean it up. Thank you for bringing those to my attention. You got 7 something. When we start spacing the bars at 2 inches instead of 1 inch on problem 4, homework 6. Wow, I've met my critic today. Jesus is going through this. Okay, so homework problem 4. Yes, I calculated I needed 7.2. And I said, let's use number 3s at 6. Did I have any other restrictions? No, no. 17, 12, or 24. That's an excellent question. Yeah, no, absolutely. Absolutely. That's a great question. That is just field experience. And so having said that, if anybody put 7 inches as their spacing on their homework, great, no problem. I am certainly not going to dock anybody for putting 7. What I was looking for really is that the required spacing per the demand, the load, was 7.2 inches. So you can't go to 8 inches, that doesn't work. But if you go to 7 inches, great, that no problem. And really, you can use 7 inches in the real world, and they probably won't be coming at you with a piece of rebar or a shovel. But after a while, you kind of just build this feel for, if you're down in the 3 to 4 to 5 inch range, you use 3 or 4 or 5 inches. But once you get up above about 6 inches, you kind of go 6, 8, 10, 12, 14, 16, and yeah, kind of like that. Does that make sense? Okay. Okay. But that's a great question. Yeah. And of course, I am certainly not going to expect somebody to be answering their homework based on years of field experience. That doesn't make any sense at all. So anybody who said 7 inches, that's totally fine. Okay, great questions. Any other questions before we get started for tonight? Okay, so if you think of anything, I'm pretty sure we're going to have a little bit of time left over after this. I don't know how much time, but I don't expect this lecture to take up a whole 2 hours, because I took the whole lecture for slender columns and broke it into 2 lectures. And we went pretty far last time. So this is really just the follow-up finishing of what we started last time. So if you guys want to, we can get started on lecture 13. What we're talking about is slender columns. And where we left off last time was we calculated the interaction equation or interaction diagram for our column in our example number 3. And we came up with this kind of simple chart. Remember, this is 1, 2, 3, 4, 5 points. So if computer software does this, they're going to calculate 200, 500 points and really smooth this thing out and get it exact. But for our purposes, this is close enough. And also remember, from a design perspective, from a procedural perspective, when we talk about slender columns, a column's slenderness does not change the diagram, okay? So a short column or a slender column or a brace column or a sway column, none of that changes this diagram. The only thing that plays into this diagram are the material properties: the size of the column, the strength of the concrete, the size of the steel, strength of the steel, and dimensioning. That's it. So this is dependent on the section properties of the column only. And now we're about to get to what you do when you go from a short column to a slender column. Okay, so now that we have this diagram, now we must calculate the amplified moments to compare the loading to the capacity. So again, like in the most basic sense, capacity-based design is always about comparing a reduced capacity to an amplified loading. And so this whole diagram is still just a graphical representation of the reduced capacity. This is phi Pn phi Mn in a graphical sort of way, but this is half of your equation. Now we're going to start the other half of the equation, the demand or the load. Okay, so we must calculate the amplified moments to compare loading to the capacity. We start by calculating the effective length of the column. Then we find psi A at the top of the column. And again, remember psi was the sum of the stiffnesses of the columns to the sum of the stiffnesses of the beams. The modulus elasticity is 57,000 times 4,000 psi is 3605 ksi. The moment of inertia for the column is 70% of I gross. I gross is BH cubed over 12, and that's 9,333 inches to the fourth. Sorry about the font here. This is IC, this is LC. But L, the length of the column from center to the top of the footing is 26 feet or 312 inches. And so psi, well, again, there's a repeat of what psi is, columns over beams. The moment of inertia of the beams is taken at 35% of I gross. So 35% of 20 times 36 to the third over 12 is 27,216 inches to the fourth. And the center to center spacing of the beams is 27 feet or 324 inches. Let me do something here real quick. This is lecture 12. Bear with me a second. No, we had already started that. Wow, finding those 5 points took a lot. There we go. That's what I'm looking for. Okay, so just so everybody, just a refresher. Let's see, no, I want slideshow, the current slide. There we go. Okay, so this is the problem statement from last time. PU is 800 kips, MU is 80 kip feet. The center to center spacing of the beam is 27 feet. The center to top of footing dimension for the column is 26 feet. And we have a pin here at the footing. And here's the section property. So I gross of the beam was 20 times 36 to the third. I gross of the column was 20 times 20 to the third. So this was our problem statement as we did a couple days ago. And then what we did is we did our 5 points to find the interaction equation for any section in the column. But now we need to figure out, is the column slender? And if so, what are our actual loading demands? Okay, so that's where these numbers come from. The I moment of inertia of the column was 20 times 20 to the third and 26 feet. And then the beam was 35% of 20 times 36 to the third, and the length of the beam was 27 feet. Okay, so assuming that the columns and beams are all poured with the same concrete, so E is the same for both columns and beams, then psi A, and this is all the columns going into that joint at the top, which is one column. Make sure we're clear about that. Okay, so psi A is at the top of the column. So how many columns frame into this joint at the top of the column? And the answer is just one. If I had another column going up above here, then I would have to have the sum of the stiffness of this column plus the sum of that column. And if I had another beam coming in from this side, then I would have the sum of the stiffness of this beam plus the sum of the stiffness of this beam. So in this case, we have one column, one beam, but you could have two columns, one beam. You could have one column, two beams, or whatever. And that's not the one I wanted. Okay, so see here how I say the sum of EI over L? Well, if I had another column going above, then you would add this to another E times I over L, and the same with the beam. Okay, so does that make sense?
Yes.
Okay, good. All right, so running this out, I get a psi A equal to 0.356. Find psi B at the bottom of the column at the footing. Well, at the bottom of the column, we defined it as a pin. So the footing itself doesn't really matter at all. We're just saying that if it is equal to a pin, we're going to use 10. Remember, we defined that psi at a pin is infinity, but the recommendation is don't use infinity because nothing ever is a perfect pin. Use 10. So that's what we're going to use. So we're going to use 0.356 at the top and 10 at the bottom at a pin connection. And so we go to our, what was this thing called? Sorry, guys, my dog is whining at me. Hold on a second. I'm going to let her out or she's just going to keep bugging me. Yeah, get her out of here. Okay, sorry about that. All right, so we're going to go to these charts, alignment charts. That's what it was. We're going to go to our alignment charts, and we're going to put in 0.36 here, and we're going to put in 10 for psi B here, and where it intersects the axis, this becomes our K value. So from the alignment chart, I'm calling this to be 0.78. Our radius of gyration is 30% of h, or 0.3 times 20 is 6 inches. So KL over R is 0.78 times the height of our column. 312 divided by radius of 6 is 40.6. That is our slenderness ratio, 40.6. Now we have to compare that to the code allowable of is it slender or is it not slender? And there's a breakpoint. So that breakpoint was 34 minus M1 over M2. Well, M2 was defined by the problem statement as 80 kip feet. M1 is equal to 0 because we have a pin at the base of the column. So this is going to then be 34 minus 0 is 34. So 40.6 greater than 34, we do have a slender column.
Professor,
Yes.
why is the 80 on the bottom? Why is it not on the top, for example?
Well, that's the equation. So if you go back to the last lecture, it was defined by ACI code that for braced columns, this is only for braced columns, but for braced columns, this check is defined as 34 minus M1 over M2.
No, my question is, how do we know that the M2 is 80? And why is not M1 not 80?
Because the code also defines that M2 is always the larger of the two.
Okay, makes
Yeah.
sense.
Yeah, I think maybe that's the answer you're looking for. It always defines, it doesn't say the top or the bottom. It always says whichever end moment is greater, that's your M2. And since you asked, I want to check on something else here. If I can find it readily. Required strength, axial columns. Balls. No, I didn't find it. Chapter. bear with me again. I just want to double check that. Oh, I know how to do that. I have the other lecture. There we are. Right there. Okay. And it is actually, okay. Yeah, I wanted to clarify this. Okay. It was a good question. So for braced columns, you compare KL over R to be less than 34 plus 12 M1 over M2, or KL over R less than 40. So even if this works out to be like 43, you're still slender if you're over 40. For unbraced or sway columns, you don't have this component, you just have a straight up 22. If KL over R is greater than 22, you have a slender column. I put it in the negative in the example because of the definition here, where M1 over M2 is negative for double curvature, M1 over M2 is positive for single curvature. That's why my example had a negative, but it really isn't double curvature or single curvature, because in my example, the base moment is 0 exactly. So it doesn't really make any difference. But I wanted to clarify that the equation, this is straight out of ACI, the equation is 34 plus M1 over M2. And by definition, M2 is the larger, M1 is the smaller, and this is absolute value too, right? So if you had minus 200 at one end and plus 100 at the other end, M2 is going to be minus 200, M1 is going to be 100. So it's the absolute value of that moment. Okay, does that make sense to everybody?
Yes, Professor. So, but for this problem, we're missing the 12, right? It was supposed to be 12 times M1 over M2. It's 34 minus 12 times M1 over M2, or?
Oh, did I forget the 12?
Yeah, because that's why I couldn't find these equations. That's why I got confused.
I would be too. Yeah. Yeah, I forgot the 12. Yep, you're right. Now, of course, in double checking my work, it didn't make any difference because we have a 0 in here, so 12 times 0 is still 0. But you're absolutely right. I'm missing the 12 right there. Yep. Okay, for everybody else, make sure we caught that right here. This is supposed to be 34 plus 12 M1 over M2. Okay, so please make a note of that. And any other questions at this point? Okay. All right, so now we have determined that we have to consider slenderness because 40.6 is greater than 34, and also because 40.6 is greater than 40. That was the other threshold, wasn't it? Let's see, where did I just put that? Yeah, so, or 40. It's either that complicated equation or 40, and in our case, we are greater than 40 and greater than 34. So definitely have to consider slenderness. When we have to consider slenderness, now we have to calculate our critical buckling load. And that's pi squared EI effective over KL squared, where EI effective is defined by ACI 318-66444 as one of A, B, or C. And A was this guy, B is this guy, or C is this guy. This one is misleading. It's actually a lot more complicated than these two. For this example, we will choose option B. Okay, so the effective stiffness, that's really what this is. Modulus times moment of inertia is stiffness. So the effective stiffness is 0.2 modulus of the concrete times I gross plus the modulus of the steel times IESE over 1 plus beta DNS. I gross, and again, we're talking about the column. So the column is 20 times 20 to the third over 12, 13,333. ISE is the moment of inertia of the pattern of rebar. So it's not the moment of inertia of one rebar about itself. That's basically nothing. It's the moment of inertia of the pattern. So you have to use the parallel axis theorem. And when you have an 8-bar pattern, let's see if I go back to, keep going back to this, but in our example, right there, and right there. Okay, so you see how all 4 bars are lined up on both sides? So from the center of the column, all 8 rebars have the same distance from the center to the center of the bar. So all 8 of them have the same effective distribution. So that's why I can take 8 times the area of 1 bar times 10 gets me to the center of a 20-inch column minus 2.5. This is my AD squared term from the parallel axis theorem. So the total area times D squared is 270 inches to the 4th. Beta DNS is the ratio of sustained load to the total load. And this was defined in the problem statement. So that equals 0.69. So I put it all together. I have 0.2 modulus of concrete, moment of inertia of concrete.
Sir, I have a question.
Yeah.
Yeah, if it's a parallel axis theorem, shouldn't there be another 8 times 0.6? That's only the AD squared to bring it to the neutral axis, but there's no.
Okay.
Or am I
No.
getting it wrong?
No. Well, let me restate it in a different way, and then you tell me if this is what you were thinking.
Yeah.
Usually, when you use the parallel axis theorem, you take the moment of inertia about its own centroidal axis plus its area times its distance to wherever you're summing it squared. So
Yes.
so you have in a rectangle, you have a BH cubed over 12 term, and then you have a BHD squared term.
Yes.
Okay, but when you're talking about rebar, the moment of inertia of a piece of rebar about its own centroidal axis is negligible. It's a fairly small circle about its own axis. We don't even bother with it. Good.
Thank you.
Does that answer your question?
Yes, thank you.
Okay. So yeah, that's what I'm saying is when you sum up the moment of inertia for the steel, the parallel axis portion of it, AD squared, is really the only part that has any significance. If you look at number 7's, the moment of inertia about its own, it's a fraction of an inch to the 4th. So we neglect that.
Okay, thank you.
Okay. So that plugs in right here. Modulus of steel plugs in here, and I divide the whole mess by 1 plus this beta DNS factor, and I get, for stiffness now, 10,321,400 kip inch squared. So then that plugs into here, and so I take pi squared times 10.3214 e to the 6th kip inch squared over 0.78 was my K. L is 312 inches, and this is squared, and I get 1,677 kips. What does this number actually represent? Is there a real significance to this number? Like a physical significance? The
Slenderness of the
physical,
column?
I'm sorry?
Is that the slenderness of the column?
Close. The slenderness of the column is down here. This length times an effective factor. This number right here, according to Euler, this is the load that it takes to take our column and just start initiating buckling. So at a load less than this, the column is not buckling. At any load above this number, the column will start to buckle. That's what this number represents. Okay, so now we need to find our moment gradient. Is defined as 0.6 minus 0.4 m1 over m2, which is 0.6 minus 0.4 times 0 over 80. We get 0.6. My moment magnification factor, delta, is defined by the code as Cm over 1 minus Pu over 0.75 P sub C. P sub C is Euler buckling. So notice right here, we got a safety factor built into this thing. We are considering the ratio of the actual load to only 75% of the buckling load. So we got a little built-in safety factor right there. So this is 0.6, and 1 minus Pu is 800 over 0.75 times 1677, and that is 1.65. M2 minimum is defined by code as Pu 0.6 plus 0.03 H, or 800 kips times 0.6 times 0.03 times 20 is 80 kip feet, which happens to be what we applied, which is equal to M2. So in other words, if M2 is defined as the problem statement as 14 kip feet, then you don't evaluate it with 14, you evaluate it with 80, because that's the minimum for these type of problems. So MC is equal to delta times M2. 1.65 times 80 is 132 kip feet. Load that causes impending buckling is more than, no, not exactly. Let me read the question. A question is the safety factor, I assume this 0.75 right there, to consider the possibility that the load that causes the impending buckling is more than you anticipated? Not so much, but I'm kind of just going off of opinion here. This is just my understanding of how they do the code. But PU has all the uncertainty of the actual magnitude of the load built into it with load factors. 1.2 dead, 1.6 live. That's built into PU. So we've got more than enough safety factor on the load side built into PU. I think what they're doing is the Euler's buckling load is very, very dependent upon the stiffness of the member. If you go back and look at how you apply Euler's buckling load to like tube steel or flat plate or anything made out of steel, it's pretty precise. But when it comes to concrete, we got this whole problem of cracking. And so even though we calculated the effective stiffness using only 20% of the stiffness of the column's concrete, and then we added in there some stiffness of the steel, even though that may not be enough. This is still pretty kind of guesstimate, kind of guessy, kind of. So if the column is even 10, 15% not as stiff as we assumed, that would dramatically affect the Euler's buckling load. So that, I think that is why, let me get back, Jack. I think that is why this delta number has this 75% on Euler's buckling load, because it's very, very dependent upon the stiffness of the concrete. And that's something that you just can't very accurately predict. Okay, so we were here. And okay, so even though we have 80 kip feet of load applied, we're going to design for 132. This is the amplified load. So that's what this whole method is. This whole method is we take the capacity of the column and we compare it to the moments that are amplified to account for slenderness. Okay, so here's my interaction diagram that I had created. And I plotted my amplified moment and axial load right in there. So does this column work or does this column not work?
The column works because it's in front.
The column,
It works. It falls in the diagram.
that is correct. So this column is acceptable. Factored load coordinate with amplified moment is still within the interaction diagram. So it works, except that we have this pesky little ACI prescription. So everything you just said is absolutely right. That's what I was looking for. But alas, section 6.2.6, delta cannot exceed 1.4. And so this beam will need, or this column will need to be redesigned to reduce that delta. So I think what they're doing is, see, this is 1.65. It can't be more than 1.4. And I think they do that because there's so much uncertainty in what it actually takes to buckle a concrete column that they just don't want, if you're amplifying it more than 40%, they basically feel that you just don't really have a good control over what this column really wants to do. So they send you back to the drawing board and say, no, make it a little bit bigger. Let's get this thing under control. So this is obscure. It's a prescription, but it is in there and you guys need to know about it. So it works according to the mechanics, but it doesn't work according to ACI prescription. Any questions about example number 3? Okie dokie. Let's talk about sway columns then. All of that was for a braced column. How does this change if you have a sway column? Well, for one, it gets a lot worse. Per ACI 318-66461, the factored design moment, M1, is equal to M1 non-sway plus delta S times M1 sway. That's what those stand for. And M2 is equal to M2 non-sway plus delta S times M2 sway. And we'll work through this, where M1 is still the lesser and M2 is the larger of each end moment. ACI 318-66462 gives the moment magnification factor as one of A, B, or C. If delta S is greater than 1.5, then only B or C are allowed. So delta S can be calculated as 1 over 1 minus Q, always greater than 1, where Q is the sum of PU delta naught VUS over L sub C. Or B, you can calculate delta S as 1 over 1 minus the sum of PU over 0.75 times the sum of PC. This is the one that's similar to the delta that we just did for brace columns. And this has to end up being greater than or equal to 1. ACI 318-66462, where delta PU is the summation of all the factored vertical loads in a story, and delta PC is the summation for all the sway resisting columns in a story. PC is calculated using equation 66442, with K determined from sway members from 66443, EI effective from 66444 or 66445 as appropriate, with beta DS substituted for beta DNS. When I wrote this part of the lecture, I had to go through these like 50 times. This part of the code is unfortunately pretty massively confusing. Hopefully I got it straight. Or if you don't want to do it using method A or method B, then you can just do a full-blown second order analysis, which is expensive and difficult, generally not done in practice. ACI section 66464 still dictates the use of a CM factor per ACI 318.6645. M1 over M2 is negative if the column is bent in single curvature and is positive if the column is bent in double curvature. Per the textbook, this CM factor should only be used if a maximum moment occurs somewhere other than one end or the other. For all other cases, take CM equal to 1.0. I know, confusing, but we'll work through an example with that. Starting now. Okay, so example 4, here's our frame. F prime C is 4,000 PSI, F sub Y is 60 KSI, and I'm using the same section properties, 20 by 20, 8 number 7s, 20 by 36 with 4 number 8s. I've got 27 feet center to center, 26 feet. This frame column is fixed to the footing. It basically would fall over if it wasn't. And I also have a factored axial load PU, and I have a factored lateral load VU, because this frame is supporting some dead load and some loads from above and a lateral load, which is coming from wind or seismic. Any questions about the setup? Okay. PU is going to be 400 kips. VU is only 6 kips. Doesn't seem like a lot, right? 6,000 pounds pushing it over. And WU is going to be taken at 1.26 kips per lineal foot. So this is a distributed load and an axial concentrated load and a lateral concentrated load. For the footing stiffness, you can assume that the subgrade modulus, K sub S, is 120 PSI per inch. And what is required, determine if the given columns are adequate with the given loading. Solution. Well, you're going to have to wait till 6 o'clock to get the solution. What do we say we take a little break and come back at 6?
Perfect.
Okay, see you at 6 o'clock. Okay, everybody. We are back. Okay, so let's get to our solution. The first step is to perform the first order analysis for the frame. The moments of inertia of the frame are reduced per ACI 318-66311 in the computer model. Okay, so that's where we use 70% for the columns and 35% of the moment of inertia for the beams. So first order analysis with non-lateral loads. Moment diagram looks like this. Basically what I did, I don't know how familiar you guys are at this point with the different software packages out there. Software packages like ETABS or SAP 2000, RISA, RAM, those are all very popular ones. Visual analysis is a popular one. And a not so well-known one is the one I use called Multiframe. But they all basically do the same thing where you build a stick frame, you give the stick frame some section properties and some restraints, put some loads on it, run it, and it will analyze the frame for you so that you don't have to do a moment distribution or a moment area or stiffness matrix analysis by hand. So much more convenient than try to analyze these things by hand. So using one of those software packages, I built the frame that we presented and I put onto it the 400 kip axial loads and I put on it the 1.26 kips per foot gravity load. And this is the resultant moment diagram for that frame. And here's our axial load. You can see 400 kips basically dominates the axial load, but I've still got 17 kips coming from the distributed load here. And I have a shear diagram where, of course, most of the shear is in the beam, but you still get a little bit of shear in the columns from the bending moment that's induced into those columns. So I just showed you the moment, axial load, and shear diagrams with no lateral loads. You separate them. So we have a gravity load case only, and then we do the lateral loads separately. Shear from the gravity loads are opposite in direction and so cancel each other. So the total story shear is 0, which it should be because we have non-lateral loads here. Okay, now our first order analysis with lateral loads. And is everybody clear what this means? What is a first order analysis versus a second order analysis? Is that clear to everybody? Anybody brave enough to tell me it is unclear to you?
It's very unclear to me.
Oh, thank you. All right. Well, see, I don't know, you know. I'm not quite sure where you guys are on all this. So anyway, thank you. What a first order analysis means is that we put this into our frame, into our software, we put the loads on it and we run it. And whatever it gives us as a result, that's it. That's our answer. But in real life, that's not the real answer. So a perfect example is if I put a lateral load on this frame and I have these big axial loads on the frame. And if I push this thing over with 6 kips, then the first order analysis only considers what you've actually applied. It doesn't consider that this whole thing has moved over by some amount. A second order analysis would push this thing over by the amount that you've pushed it over, but then it looks at it and says, oh, well, this axial load is now this much farther from the center of the reaction down here. That causes more bending, which is going to cause more deflection. And so it iterates, and it does this like thousands and thousands of iterations until either the whole frame settles at some new location, which includes the effects of P delta, or it doesn't converge at all and the whole thing just fell over, which could happen. So a first order analysis does not take into account that anything has moved. It doesn't look at this axial load shoved over by so many inches. It ignores that. It just simply runs through the stiffness matrix and solves for deformations and rotations, shears, moments, and axial loads. Is that better or is that worse?
Much better. Thank you.
Okay. All right. So that's the definition of a first order analysis. And the code says, go ahead and just do the first order. That's good enough. So we did our first order analysis with just gravity loads. Now we're going to do it again with lateral loads. So the moment diagram with lateral loads, you see these moments got much bigger. We're 37 here, 41 here, whereas with just gravity, we were at 31 and 16. So it's particularly at the bottom of the column, the moments got much bigger because you're trying to push this over and it is bending that's keeping it from falling over. Also, the shear was only 1.8 kips. With the lateral loads, well, the axial load diagram almost goes to 0 if I take away all the gravity load and I'm just looking at lateral load. I do have a little couple here that resists the global bending of the whole frame bending over. And here's my shear diagram where basically the 6 kips that I'm pushing it over, some of it went to this leg, some of it went to that leg, pretty evenly divided. Okay, so does that make sense to everybody? I had to analyze the frame twice, once with gravity loads and again with just the lateral load. Okay, so now we're going to look at first order deformations. So from my lateral load, when I applied that 6 kips, based on an elastic analysis, so we're not doing anything funny here. This is just a straight up elastic analysis, but I am using 70% of the column's moment of inertia, 35% of the beam's moment of inertia, and the top of this frame bent over 0.214 inches. That is my lateral deformation from the applied load. So now we need to test, is the frame sway or non-sway? And we can use it where Q is the sum of PU over delta naught VUS LC. Sigma PU is a sum of all factored axial loads for the story. So that was 417 plus 417. And that came from right here. Axial load on this column, axial load on that column. We're adding up the whole story. If you had a fairly large building, that could be tens or hundreds of columns that you're adding up. You're just adding up the sum for the whole story. This is a really simple bent frame, so it's just 2 columns. Okay, so the sum of that is 834 kips. VUS is the total lateral load for the story. That was defined in the problem as 6 kips. Delta naught is the first order relative lateral deflection due to VUS. That was my 0.214 inches that we just found. And LC is the height of the story, measures center of joint to center of joint, which in this case is to the top of the footing, so that's 26 feet or 312 inches. So Q is equal to 834.214, 6 kips, 312, 0.095. This is greater than 0.05, which is the code's threshold for slenderness, or I'm sorry, not slenderness, for sway. So because Q is greater than 0.005, this column is considered a sway column. And we kind of knew that anyway, because it's the only thing holding up that frame. There is no wall or brace frame or anything else providing stiffness. It is just the columns on their own. But this is just a confirmation that this would be considered a sway column. Next, we calculate the effective length of the column. By the way, any questions about this? Okay. Next, what we do is we calculate the effective length of the column. And we have to find psi at the top of the column. This is going to be the same routine as we did before. In fact, they're all the same numbers, except now we have this beta ds, ratio of sustained shear to total shear, which is 0. None of the shear is going to be sustained. It's all, basically in this case, it'd be seismic.
Professor?
Yeah.
Where'd you get the 0.214 inch from? I couldn't find that.
That was from my frame analysis.
I can't find that.
Okay.
No. Oh, never mind. Got it. Never mind.
Well, I'm there anyway.
Yeah,
Right there.
Yeah, sorry about that. Yeah. The couple of zeros on the side, I was very confused.
Yeah. I'm sorry about that. That's how it reports it. But this is what it's doing to explain the zeros. This is the deformation in the X. This is the deformation in the Y. And the last zero is the deformation in Z. And Z is in and out of the page, so it's absolutely 0. That's why it's a confusing number because it's reporting 3 coordinates. But the number that we're honed in on is the 214 right there.
Makes sense. Thank you.
Okay, so IC is equal to IC over 1 minus beta ds, but beta ds in this case is 0. So my effective moment of inertia is still 93.33 inches to the 4th. And my effective length of the column is 312 inches. And moment of inertia of the beam is 35%, as we did before. So we got the same numbers here, 27,216. The beam is 27 feet long, or 324 inches. So psi A is 0.356, very similar to what we had before. Now psi B at the bottom of the column at the footing, here we have to calculate the stiffness of the footing. So for the footing moment of inertia, h is the plane dimension in the direction of the frame. And so that I'm using the same footing as we used from last lecture, which is a 6 foot by 8 foot footing, but it's 6 feet times 8 to the 3rd over 12, which is a big number, 5,308,400. And case of S, the modulus of subgrade reaction is 0.12 KSI per inch. So psi B, plug in all the values, and we have 0.677. So this number can vary quite a bit. Remember, if it's pinned, we consider it to be 10. If it's fixed, we consider it to be, I think it was 0.1. So this number can vary quite a bit depending upon the flexibility of the footing versus the flexibility of the column itself. Now we're going to go back to our alignment charts, but this time you have to go to the unbraced frames, not the braced frames. Makes a huge difference. And so I plug in my 0.356 and my 0.6 something that I just had. And I read off the chart here, and I get a K value of 1.16. Radius of gyration is 6 inches as before, so my KL over R ratio is 60.3. That's pretty slender. And remember, for sway columns, compare it against 22, not 40, 22. And so 60.3 is quite a bit more than 22. Therefore, slenderness must be considered for this column. Any questions at this point?
Professor,
Mhm.
could we say that the BDS is 0 because it's not braced? Is that a possible way of thinking about it?
No.
Okay.
Beta ds or beta dsn is the ratio of sustained to total. So there are some places in this whole procedure where you look at the ratio of sustained axial load to total axial load, and it's not going to be 0. It's never going to be 0 at that point. But at other points in this procedure, you look at sustained shear versus total shear. And usually shear is coming from some environmental factor that is not sustained, wind or seismic. Neither of those two are sustained. So yeah, you gotta be careful about that factor.
Okay, makes sense. Thank you.
Okay, so therefore slenderness must be considered. 60 is much greater than 22. So we calculate our Euler's critical buckling load as we did before, where, and I'm going to use the same formulation I did before, but here's what I was just talking about. Now beta ds for sway is ratio of sustained shear over total shear, not axial load over total axial load, which changes EI effective pretty dramatically. So I gross is still 13,333. ISE is 270 like we did before. Beta ds is 0 over 12 kips. Actually, the total story share is 6 kips. That's another typo. But still, anyway, 0 over 6, 0 over 12, still 0. Beta ds is 0. So your effective stiffness is going to be, this is all the same as before, but now we're just over 1. And that gives you 17,443,100 kip inch squared. So my Euler buckling load, I take this, plug it in here. My K is 1.16, my length is 312, and I get 1,314 kips. So it is pretty dramatically different than the 1677 we got before. And the only difference so far is this K factor and this beta ds factor. So these things swing a lot. You got to be very careful about every one of these components that goes into these. Okay, so delta S is defined as 1 over 1 minus sum of PU over 0.75 sum of PC. So I have 2 times 417 kips as the axial load, and I have 2 times 1314 is my Euler critical buckling load, because there's 2 columns in this frame. And so I get a delta S of 1.73. M2 minimum is my PU times a minimum, 817 is the total axial load. So I get 81.7 kip feet as my minimum. Let me double check that. That doesn't spell right. 0.03 times 20 plus 0.6 times 81.7. Nope, 81.7 kip feet. Okay. Which is less than M2. Now remember, M2 in this case was given from the moment diagram that I showed you. I think it was somewhere around 40. So what controls is the 81.7 as a minimum. Okay, so my design load, we're finally getting somewhere here. My design load M2 is equal to M2 non-sway plus delta S times M2 sway. And these numbers, 3183 and 3681, come from those 2 moment diagrams that I showed you previously. One moment diagram was just with gravity load, this guy, and the other moment diagram was just from lateral load, this guy. So now I add them together with this delta S factor, and these two together equal 95.5 kip feet. Mu over M2 is 95.5 over 3183 plus 3681. These are directly from the analysis, and this is the one that's amplified. And so my amplification net is 1.39. Less, or I'm sorry, that's supposed to be less than 1.4. So I still have this 1.4 restriction, but it's not on delta S, which was 1.73. It's on a total effective amplification. So my design load divided by my first order design load is still just under 1.4, so we're okay. Column interaction diagram. Hey, guys happy? We don't have to do it again. We're going to use the same column as from example 3. So there's the diagram we created from example 3. And onto this diagram, we plot our load, 95.5 and 417. And there it is right there. Since the magnified load still fits within the interaction diagram, then the design is acceptable. And we met that 1.4 criteria, so therefore it is acceptable as well. In the real world design, all load cases would need to be evaluated. Yeah, here we only did one. We did one load case, but in the real world, you could have many, many different cases. You could have skip live loading, you could have 1.4 dead or 1.2 dead plus 1.6 live, or you could have 1.2 plus 0.2 SDS dead plus the seismic lateral load on there. At some point, you start needing software just to kind of get your hands around all these things. But principle-wise, this is the principle. Our amplified load is still inside the interaction diagram, so this particular load would still be acceptable. And lastly, I took the very same column that we did by hand, and I analyzed it with a software program. Put in here, one of these was just the dead load, and one of them was amplified for that slenderness factor, and they fall within the diagram, so therefore the designs are adequate. Okay, so that concludes our slender columns. Do we have any questions?
Gonna have to run through these examples and maybe compile some questions if anything. For now, I don't have questions.
Fair enough. Fair enough. We still have, what, 4 more lectures? So we have 4 more office hours. And like I said, we're probably going to have quite a bit of time on that last Thursday, the last day of school. So we can always come back to some of these things if you have questions. But anything else in the presentation that didn't make any sense or anything else?
Professor, for these questions for this column question, we're not using SAP or any other software. How would we solve it during the exam?
Well, you're not. You're not going to solve it during the exam. Right? So let's go back to example. Here we are. Let's go back to this. Okay. Yeah, there's no way I'm going to ask you to do a column frame analysis and come up with your first order moments and shears and axial loads in a test situation. I can't do that. But I can still test you on this material. There's all kinds of ways that I can diabolically create a nasty test that would fairly test your knowledge of the subject matter without making you go through what took me 125 slides to do as an example, right? So, I mean, there's all kinds of interesting and fun ways that I can test you on this material without actually saying, here's a frame, design the whole thing, right? So here's a frame. Are these columns okay? Or even worse, right? Here's a frame, here's the loads. Tell me how much steel I need in these columns. No, that'd take you like 5 hours to do just one problem. So we're not going to do that. But we are going to make it in such a way that we test your knowledge of the subject. We may not even do a sway frame cylinder. I don't know. I'm not sure what we're going to test you on, but you should at least, study the material and be somewhat aware of what's going on with it. But in all practicality, no, we can't do a frame analysis on a test problem.
Okay, thank you. And could you, like later on, if we have time, could you give us some example of what to expect on final, if it's possible?
Well, what's going to be on the finals is like what we're doing in the homeworks. I think that's your best indication of what might be on the final is similar to what we would do in the homeworks.
Okay, thank you.
And then, of course, if we have extra time on the last class, most certainly we're going to dedicate some time to going into more detail about what is going to be on the final.
Okay, thank you.
Sure. Any other questions? I mean, if you want to talk about the final now, but I haven't written it yet, so I'll know much more about it on that last class. But I mean, I still owe you half an hour. I'm being paid by the hour here. So if you have any other questions, by all means. And no, I'm not being paid by the hour.
Professor, also, the way the syllabus is like little stressful to us, I think. Like 40% on midterm and final. Do you think we can anyhow boost our grades, like if you can give us like extra credit question on final, or somehow offer us something so we can, whoever wants to, he or she can boost the grade?
I don't typically do that. The whole point of the way that I structure the grading system and the points is to make sure everybody is actively working on this course each week. Really, what happens is you don't want people to just kind of tune in and tune out, and then 2 days before the midterm, try to cram it all back in. So really the way that it's structured is to have everybody learning as you go along. I don't do quizzes, and I don't really have a lot of extra credit. Sometimes I'll put a few little extra credit questions on a test. Sometimes I do, sometimes I don't. But they're just like fill in the blank type questions to make sure that you're listening and paid attention during the lectures, and you get a little bonus for that. I've been known to do that. But mostly, I would say the students that have had me before, it's in the curving that I make the course fair in the curving. And what I mean by fair is that if I didn't cover something very clearly, and everybody in the class, except for a few, maybe a few got it, but most people in the class missed that D from the top of the beam to the lowest layer of the steel is D sub T, but D to the center of all the steel is D, and those are different, and that wasn't really clear. And when you calculate epsilon sub t, you have to use d sub t. That wasn't really clear. Then everybody loses a point. Almost everybody loses a point in the same place. Okay, well, that's a clear indication that I didn't cover it adequately. I breezed over too quickly, or it wasn't clear. So that's what the curving is for. The curving is there so that all boats rise with a rising tide. If I did something that was confusing to just about everybody, then I make up for that in the curving so that I don't have like everybody loses 2 or 3% of their total grade because I failed to adequately explain something. That's how I bump that back up. So not so much an extra credit, maybe not, a little bit on the last test, but really just keep up on your homework and do your best on these tests and you should be fine. But hopefully that answers that question.
Yeah, thank you so much.
Okay, anybody else anxious or jittery about the final? Anything else you want to talk about? I will offer, I mean, really, we're not supposed to teach to the test, right? That it really, my job is to expose you to the amazing and wonderful world of concrete design, and then just make sure I test you so that you've soaked up enough of it that you're somewhat competent in it in what, you know, the goals of the course are. But I will tell you as a tip, as a guide, that what I ask for you from the homeworks, as you probably have noticed by now, are much more mechanical. They are asking you more fundamental mechanical questions, like what is the moment capacity of this beam? Or what is this good for in shear? Or, you know, some like real world capacity-based or design-based questions. I don't spend a lot of time in the homework asking you to recite all those prescriptions about column design in seismic country. So the prescriptive part of the code is very important, and I do hit on it a lot. As you know, I absolutely insist, do your minimum steel checks, your maximum steel checks, your beam width check, your FIAMIN greater than MU checks. You know, I'm very strict about that because those are very important. But let's face it, the ACI code is like, what are we up to, like 600 pages or so? The tests are not going to be so heavy on all these prescriptive things in the code. They're going to be more based on fundamentals, like what I'm asking you to do on the homework. But that don't take that to say that none of it's going to be from the code, because I want you to tell me what epsilon sub t equals and what is phi equal. Those, you have to know that from the code. But I'm not going to go ad nauseum about tie spacing regulations and all kinds of prescriptive things from column design when I didn't even ask you to do that in the homework. So long story short, pretty much what I'm asking you to do on the homeworks is what's fair game for the test. And the best way to study for the test is to go back and re-look at your homeworks and do some more problems and work through examples like you see in the text or like I've presented in the lectures. And that's really the best way to study for the test.
Right on.
Okay. Is there anything else I can say? Is there anything else I can help with at this time?
Professor. Professor, if we have
Yes.
extra time, we're not going to go to the next lecture, or are we going to go to the next lecture right now? Or
No, we're going to call it for today. Yeah.
could you please briefly? I know you did explain the BDS for me, But for the second one, I 100% got it because it was over 6. It was 0 over 6. That one was very simple. Sorry, for the second one. For the first one, when we still said it was 0, but there was no equation behind it, what would be the equation for it when saying the ratio of sustained shear to total shear? And
Okay.
yeah, I just want to know what the equation behind it is.
Well, no, it's just, okay, no, good question, good question. Let me find it. Let me answer it properly. Where did we have that little booger? I think it was in, wasn't there? No, it was in the moment of inertia. What it does is it modifies the moment of inertia. There it is, right there. Okay, so that's beta DNS. NS of the DNS, NS stands for non-sway. So you have a beta DNS or you have a beta DS. So for DNS, it is representative of the sustained axial load over the total axial load. For beta DS, it is the sustained shear over the total shear. Okay, so one's axial, one is shear. Okay, so where I did that was right in here somewhere. Right there. I see it. I see it. Let me isolate it. Okay, so beta DNS, you're right. I didn't put like the variables here, but what it is this is the axial load sustained over the total axial load. And where that comes from, was that the last? No.
I believe that was from the last lecture. It said on the last lecture.
Oh, yeah. You're right. You're right.
That PU equals 800K. And
there it is, right there. Yep. So PU is 800K and 550 of it is sustained. So really what that's saying is the dead load, factored dead load is 550 kips, but the total factored load, which includes live load, is 800 kips. So the ratio is 550 over 800. So when I got to today's lecture, I lost that point, didn't I? It was down here, right in here. So close, right there. Okay, so beta DNS is the sustained axial load over the total axial load. But in the sway column, example number 4, it's the sustained shear over the total shear. And in this case, and in most cases, the sustained shear was equal to 0.
So, but if the sustained shear was not equal to 0, will we have like a parenthesis saying how much of it got sustained?
I'm sorry, last part?
Like for example, in example 4, I mean, like I'm trying to compare example 3 to example 4.
Yes.
So in example 3, we had the parentheses that said sustain of it was 550.
Yes.
So for example 4, does the same follow? Do we have to have like a parenthesis that says, for example, out of the 6, 2 kips got sustained?
Okay. I didn't think of it that way. I guess I could have done it that way. I didn't think of it that way because it is so rare that any of it would be sustained. Because usually, and now we're not talking about the shear on one column, we're talking about the shear across the whole building at that floor level. So we're like between the ground floor and the first floor, the total story shear across the whole building. So even, and I wanted to make that distinction because, and I don't want to lose that train of thought. Let me find my shear diagrams. Okay, here's my sway example. And here's my shear diagram. Okay, so you see, I have some shear in these columns due to gravity load. There's, because the gravity load tries to bend this beam, which tries to bend the columns out. When you bend the columns out, every bending moment has to have a shear. So this is the shear associated with the bending moment, but they are opposite in direction. So for the whole story, the shear is 0 because each one of these cancels the other one out. So that's what I'm saying. I'm being very clear that for beta dn or beta ds, it is the total story shear, not the shear at one column. So how do you get a sustained story shear when these bending moments cause some column shear, but they totally cancel each other out? What would actually create a sustained story shear? Well, one example would be if you had a building that is subterranean by some degree, and you have concrete walls around it retaining dirt. And so now the dirt forces are shoving the building over, and you have some shear in your building resisting the load from that dirt. And that load would pretty much be sustained all the time. The dirt would always be pushing up against your building. But how rare is that? You don't really get that a lot. So that's kind of like one of the few examples I can even think of where you have a sustained shear in your story. Most of the shear, I mean most of the shear is going to be from wind or seismic, or I suppose there's other ways you could get shear from like a transient loading from I don't know, maybe like you have a bent frame and this is supporting a railroad train or something like that. But even then, that would not be sustained. So really, for all intents and purposes, beta ds almost always is 0.
That clarified everything. Thank you so much.
Great, cool. Okay. Anybody else? Any questions? Okay. And if you have questions and you just are not comfortable in this forum, you can email them to me, or you can log in for our office hours that are the hour before this class next Tuesday, or you could chat it, or there's any number of ways that you could ask questions. If you're doing homework over the weekend, you have questions, best way is just send me an email and I will try to get it when I can. And so if there are no further discussions, we'll go ahead and end it for the night. Thank you, everybody.
Thank you, Professor.